The 3rd of November, 2025, 3:47 Universal Coordinated Time. Deep in the control room at Goddard Space Flight Center, something impossible begins to happen. The Hubble Space Telescope, humanity's most famous eye on the cosmos, stops responding. Not a gradual decline, not a predictable system failure, but an instant severance of communication. The screens displaying real-time telemetry from the aging observatory simply go dark. Mission controllers exchange nervous glances. Hubble has survived over 3 decades in orbit through countless anomalies and near-death experiences. The engineering team has protocols for every conceivable failure mode. But this shutdown carries a signature they've never encountered: clean, complete, and utterly unexplained. 11 minutes later, the James Webb Space Telescope experiences what NASA will later describe as a communications array malfunction. JWST, the $10 billion infrared observatory, positioned nearly 1 million miles from Earth, falls silent mid-observation. The target it was studying at that precise moment, 3I Atlas, the massive interstellar visitor that's been puzzling astronomers since its discovery in July. 3 minutes after that, the Chandra X-ray Observatory reports an unexpected thermal event. Systems go offline for what technicians term protective measures. 3 separate satellites, 3 different orbital positions, 3 simultaneous failures within a 14-minute window. The odds of this occurring by chance? Astronomical. What makes this cascade of technical difficulties truly disturbing isn't the timing alone. It's what these telescopes were doing when they went dark. All 3 were tracking the same object as it moved through a specific region of space, executing what had been planned as a coordinated observation campaign. Months of preparation, hundreds of hours of allocated telescope time, all designed to capture 3I Atlas during a critical phase of its journey through the inner solar system. The blackout lasts 72 hours, 3 days when the most sophisticated instruments ever built by human civilization sit idle, blind to whatever 3I Atlas is doing during its most active period. Ground controllers work around the clock, running diagnostics, checking backup systems, attempting to restore communications. Nothing works until suddenly, inexplicably, everything does. On November 11th, systems begin recovering. Hubble's gyroscopes recalibrate themselves. JWST's communications array starts functioning normally. Chandra's thermal readings return to nominal ranges. No engineering intervention required. The satellites simply wake up, as if from a planned sleep cycle that nobody scheduled. Mission teams immediately request the stored data from those 72 hours. Every space telescope has buffer systems, redundant storage designed to preserve observations, even during communication blackouts. But when engineers access these buffers, they find corruption. Not random bit errors or explainable data loss, but systematic corruption that renders the stored observations completely unrecoverable. 3 days of continuous observation during 3I Atlas's most dynamic period, gone. NASA's official statement cites gyroscope calibration issues, routine communications maintenance, and coincidental thermal management events. The explanation satisfies exactly nobody who understands orbital mechanics and spacecraft operations. 72 hours of darkness, and when the light returns, the most important data humanity has ever attempted to collect simply doesn't exist anymore. 4 months before the blackout, on the first day of July 2025, astronomers at the Atlas facility in Chile capture something that violates every expectation about interstellar space. The automated survey system flags an object moving against the stellar background, trajectory and velocity completely wrong for anything born in our solar system. Within days, the Minor Planet Center confirms what the Discovery team already suspects. This is the third interstellar visitor ever detected by human civilization. They designate it C/2025 N1, but everyone simply calls it 3I Atlas. The 3I means third interstellar, a reminder of how profoundly rare these cosmic wanderers are. Only 2 others have passed through our neighborhood in recorded history. But as observatories worldwide begin tracking this latest visitor, measurements start revealing something deeply troubling. The object is massive, not merely large, but impossibly, incomprehensibly massive. Initial estimates suggest a minimum weight of 33 trillion kilograms, roughly equivalent to 40,000 Empire State Buildings, compressed into a single cosmic snowball. The nucleus spans at least 5 kilometers in diameter, making it orders of magnitude bigger than the previous interstellar visitors that captured headlines in recent years. Size alone wouldn't necessarily trigger alarm bells. The universe contains plenty of large objects. What makes 3I Atlas genuinely anomalous is how it moves through space despite that tremendous mass. Telescopes observe active gas jets streaming from its surface, water vapor and carbon dioxide erupting as solar heating warms the ancient ice. This is normal comet behavior, the kind of outgassing astronomers have documented thousands of times in solar system comets. But here's where physics starts breaking down. When gas escapes from a comet's surface, it creates tiny rocket forces that push the nucleus in the opposite direction. This effect is predictable, measurable, and observed in every active comet ever studied. Astronomers can calculate expected acceleration based on how much gas is escaping and how fast it's moving. The mathematics are straightforward, the physics ironclad. 3I Atlas shows virtually no acceleration from its gas jets. The expected orbital nudge simply isn't there. 4,022 positional measurements from 227 observatories worldwide confirm the same impossible result: active outgassing without corresponding acceleration. It's like watching someone try to move a freight train by throwing tennis balls at it. The balls bounce off, the train doesn't budge, and observers realize they're dealing with something far more substantial than appearances suggest. Either the laws of momentum conservation are negotiable, which they're not, or 3I Atlas possesses mass so enormous that its own breath can't move it. The universe has presented astronomers with an object that looks like a comet, breathes like a comet, but shrugs off its own exhaust like a mountain ignoring morning mist. Something fundamental about this visitor doesn't add up. The public discovery announcement comes on July 1st, 2025, but the real story begins 48 hours earlier in a series of encrypted communications between observatory directors across 3 continents. Before press releases, before official designations, before the astronomical community at large learns about 3I Atlas, a small group of researchers sees something in the preliminary data that makes them reach for secure phone lines instead of standard email channels. The earliest tracking images show orbital characteristics that trigger immediate concern among veterans who've spent decades studying solar system dynamics. The object's trajectory carries an inclination of just 4.1 degrees relative to the ecliptic plane, the flat disk where Earth and other planets orbit the Sun. For objects arriving from random interstellar directions, this alignment occurs naturally in roughly 1 case out of 500. Possible, certainly, but statistically uncomfortable. But trajectory alone doesn't explain the late-night conversations between Harvard's Center for Astrophysics and the European Space Agency's Operations Center. What drives these urgent consultations are the spectroscopic signatures captured during the first week of observation. Early infrared measurements reveal thermal properties that don't match any comet profile in the existing databases. The object radiates heat in patterns suggesting internal temperature distributions fundamentally different from what sublimating ice should produce. By mid-July, 3 separate research teams working independently arrive at similar preliminary mass estimates. All 3 teams hesitate to publish. The numbers they're calculating seem too extreme, too far outside the expected range for interstellar debris. Publishing mass estimates that suggest something 30 to 50 times heavier than previous interstellar visitors risks professional credibility. Better to wait for more data, better instrumentation, independent confirmation. The hesitation proves prophetic. When the James Webb Space Telescope turns its infrared spectrograph toward 3I Atlas. In early August, the chemistry data creates what one researcher later describes as a crisis of interpretation. Carbon dioxide ratios exceed anything observed in solar system comets at comparable distances from the Sun. The enrichment levels suggest formation temperatures below -125 degrees Celsius. Conditions so extreme, they challenge current models of how icy bodies form in stellar systems. Observatory scheduling committees begin receiving unusual requests. Telescope time proposals marked urgent, observation windows demanded with higher priority than typical scientific protocols allow. Facilities designed for routine surveys suddenly find themselves recalibrating instruments for tracking a single target. The coordination happens quietly, without public fanfare, but the pattern reveals something important. Experts are worried. What troubles these early observers isn't any single measurement. Individual anomalies can always be explained away through measurement error, instrumental artifacts, or simple bad luck. What creates genuine concern is the accumulation, unlikely trajectory, plus unusual thermal signature, plus extreme chemistry, plus anomalous mass estimates. Each piece might be dismissed independently. Together, they form a pattern that experienced astronomers recognize as significant. By late July, before most of the world has even heard of 3I Atlas, a small community of researchers already suspects they're not dealing with an ordinary interstellar comet. They just don't know yet how extraordinary it will prove to be. The precision required to understand 3I Atlas pushes ground-based astronomy to its absolute limits. Between May 15th and September 23rd, 2025, observatories scattered across every continent collect 4,022 individual positional measurements. 227 separate facilities contribute data, creating the most comprehensive tracking campaign ever mounted for an interstellar visitor. Each measurement locates the object against the background stars with accuracy approaching a fraction of an arcsecond, roughly equivalent to spotting a coin from 20 kilometers away. These thousands of data points converge on a single, deeply uncomfortable conclusion. The lower limit for 3I Atlas's mass sits at 33 billion tons, a number so extreme it initially seems like a calculation error. Researchers run the analysis multiple times using different mathematical approaches. The result doesn't change. If anything, more precise measurements make the mass estimate climb higher. Here's why this number breaks conventional understanding. Mass estimates for comets typically rely on measuring how their own gas jets push them around. When ice sublimates into gas and escapes from the surface, it creates tiny rocket forces that nudge the parent body. These non-gravitational accelerations appear as small deviations from pure gravitational motion, subtle but measurable effects that accumulate over weeks and months of observation. The expected acceleration for an object showing 3I Atlas's level of activity should be easily detectable. Gas production rates, estimated at roughly 150 kilograms per second, moving at velocities around 440 meters per second, ought to create obvious orbital perturbations. The mathematics are straightforward. Momentum must be conserved, so escaping gas transfers momentum to the solid nucleus. But 4 months of precision tracking reveals acceleration below 15 meters per day squared, essentially indistinguishable from pure gravitational motion. This upper limit sits so low that most solar system comets would show 10 to 100 times stronger effects given similar activity levels. The disconnect between visible gas production and missing orbital response creates a paradox that has only one conventional resolution: enormous mass. Using typical comet densities, around 500 kilograms per cubic meter, the 33 billion ton lower limit translates to a nucleus diameter of at least 5 kilometers. For perspective, the previous interstellar visitor, called 2I Borisov, had a nucleus roughly 1 kilometer across. 3I Atlas potentially outweighs its predecessor by factors of 10 to 1,000, jumping from pebbles to boulders in the cosmic debris field. The mass paradox gets worse under scrutiny. Larger masses should correlate with easier detection, since bigger objects reflect more sunlight and survive longer journeys through interstellar space. Population statistics predict we should find dozens of smaller visitors before encountering something this massive. Yet here stands 3I Atlas as only the third confirmed interstellar object ever detected, defying every reasonable expectation about discovery order. Something fundamental about the physics isn't working. Either the gas production estimates are completely wrong, which seems unlikely given spectroscopic confirmation from multiple instruments, or the acceleration measurements contain systematic errors, which extensive cross-checking rules out, or 3I Atlas genuinely possesses mass so tremendous that its own breath can't move it, like trying to propel a battleship with a desk fan. The numbers refuse to cooperate with conventional explanation. Mathematics has a way of revealing uncomfortable truths that casual observation might miss. When astronomers begin calculating the probability of 3I Atlas appearing exactly when and where it did, the numbers paint a picture so statistically improbable that it demands explanation beyond simple cosmic coincidence. Start with the orbital alignment. 3I Atlas approaches the inner solar system with an inclination of just 4.1 degrees relative to the ecliptic plane, the flat disk containing Earth's orbit and most other planets. Objects arriving from random interstellar directions should show inclinations distributed across all possible angles. The probability of achieving alignment this close to the ecliptic by pure chance, roughly 1 in 500, uncomfortable but not impossible. Plenty of events with 500 to 1 odds occur every day. A single unlikely occurrence doesn't necessarily indicate anything more than luck. But 3i Atlas doesn't stop at one statistical anomaly. Consider the discovery order problem. Planetary systems eject debris through gravitational scattering, with smaller objects launched more easily than massive ones. Simple physics dictates that interstellar space should contain far more kilometer-sized objects than 5-kilometer giants. Detection capabilities favor finding numerous small visitors before encountering rare massive specimens. Yet 3i Atlas, potentially the heaviest interstellar object by factors of 10 to 1,000, appears as only the 3rd confirmed visitor. The probability of discovering such an extreme outlier this early in systematic surveys, conservatively, 1 in several thousand. Now examine the chemical signatures. The carbon dioxide to water ratio detected by the James Webb Space Telescope ranks among the highest ever measured in any comet at this distance from the Sun. This enrichment indicates formation in stellar system regions colder than -125 degrees Celsius, beyond what astronomers call the carbon dioxide snowline. Most comets form closer to their parent stars, where water ice dominates. The fraction of interstellar visitors that should carry such extreme chemistry, perhaps 1 in hundreds. Layer on the timing. 3i Atlas arrives during the narrow historical window when human technology has just achieved the capability for detailed interstellar object characterization. 20 years earlier, we'd have missed it entirely, or captured only crude data. 20 years later would add nothing to current capabilities. The object appears precisely when we can study it, but before we can intercept it. Calculate the odds of this temporal coincidence, millions to 1 against. Multiply these independent probabilities together. 1 in 500 for the trajectory alignment, 1 in thousands for the mass discovery order, 1 in hundreds for the chemistry profile, 1 in millions for the detection timing. The combined probability becomes so small that statistical frameworks start breaking down. We're discussing events that should occur once in tens of millions of similar scenarios. 2 interpretations emerge from this statistical assassination. Either we're witnessing the astronomical equivalent of winning the lottery while being struck by lightning during a solar eclipse, or the apparently random factors aren't random at all. Coincidences. This extreme force consideration of alternatives to pure chance. When unlikely events accumulate beyond reasonable thresholds, scientists face an uncomfortable obligation to examine whether underlying assumptions about randomness remain valid. 3i Atlas passes that threshold decisively. The mathematics don't prove intent or design, but they absolutely demand we ask whether something beyond cosmic dice rolling is operating here. Sometimes, the universe's most important messages arrive written in the language of improbability. July 21st, 2025. The Hubble Space Telescope, humanity's most iconic orbital observatory, completes a scheduled imaging sequence of 3i Atlas. The data transmission begins at 1400 hours Universal Time. Raw image files flowing down to the Space Telescope Science Institute in Baltimore. What arrives in those digital packets will fundamentally change the conversation about this interstellar visitor. The photo analysis team expects to see a typical comet. Bright nucleus surrounded by a diffuse coma, with dust and gas streaming away from the sun in the classic tail configuration. Comets have looked essentially the same through telescopes for centuries. Solar radiation and stellar wind push material outward, creating the iconic streaming appearance that ancient astronomers interpreted as celestial omens. 3I Atlas refuses to cooperate with expectations. The visible light images reveal what observers immediately describe as a teardrop-shaped cocoon, already unusual enough to warrant detailed examination. But the feature that makes the team go silent is the pronounced glow pointing toward the sun rather than away from it. This forward-directed brightness, what astronomers call an anti-tail, violates the basic intuition that comet debris should be pushed away from our star, not toward it. Anti-tails aren't completely unprecedented in solar system comets. They can result from viewing geometry, where Earth's position creates an optical illusion of sunward-pointing material. Larger dust particles following ballistic trajectories sometimes create similar effects, but those explanations require specific geometric conditions that change as orbital positions shift. The anti-tail in 3I Atlas shows prominence and persistence that push beyond comfortable explanations. The visible light images are strange enough, but when analysts examine the infrared data, the strangeness deepens. Thermal signatures don't match standard comet profiles. The temperature distribution across the coma suggests heat sources beyond simple solar warming and radioactive decay. The pattern looks almost regulated, as if internal processes are maintaining specific thermal characteristics rather than passively responding to external heating. Most disturbing to the analysis team, the raw data sits on classified servers for 2 weeks before limited public release. This delay isn't standard procedure for Hubble observations. Typical processing and release schedules run days, not weeks. The gap raises questions about what additional analysis occurs during those 14 days. What are researchers looking for? What might they have found that requires careful consideration before public disclosure? When the images finally reach the broader astronomical community, they trigger immediate demands for follow-up observations. Gemini South Telescope in Chile prioritizes 3I Atlas for high-resolution imaging. The Very Large Telescope arrays in Chile and the Canary Islands allocate emergency observation time. Everyone wants to confirm what Hubble saw and understand what it means. The teardrop cocoon and sunward glow become the first widely visible evidence that 3I Atlas isn't behaving like a normal comet. The mass paradox had been buried in technical papers and orbital mechanics calculations that only specialists could appreciate. But Hubble's images provide something anyone can see, an object that looks wrong. The visual evidence makes the anomaly undeniable and accessible. Something about this visitor challenges the fundamental assumptions astronomers hold about how icy bodies should behave in interplanetary space. The images don't prove artificial origins or exotic physics, but they absolutely prove that conventional explanations need serious reconsideration. The universe has sent something unusual, and Hubble has given us our first clear look at just how unusual it is. August 6th, 2025, the James Webb Space Telescope, the most expensive and sophisticated infrared observatory ever constructed, turns its near-infrared spectrograph toward 3I Atlas. JWST cost $10 billion and represents the pinnacle of human astronomical capability. Designed specifically to peer into the chemical composition of distant objects through spectroscopic analysis. What its instruments detect this day creates what the science team will privately describe as a crisis of interpretation. Spectroscopy works by splitting light into its component wavelengths, revealing the unique fingerprints of different molecules and atoms. Every chemical compound absorbs and emits light at specific wavelengths, creating patterns as distinctive as human fingerprints. When JWST examines 3I Atlas, it finds fingerprints that shouldn't exist together in nature. The spectrograph detects water ice and water vapor, exactly as expected for a comet warming in sunlight. Carbon monoxide appears in reasonable proportions, another unsurprising finding. But the carbon dioxide measurements stop the analysis team cold. The ratio of carbon dioxide to water exceeds anything observed in solar system comets at comparable distances from the Sun. The enrichment isn't modest, it's extreme, ranking among the highest measurements ever recorded. This chemical signature points toward formation conditions that challenge current understanding of how icy bodies develop in stellar systems. Carbon dioxide only freezes solid at temperatures below -125 degrees Celsius. Finding such high concentrations relative to water suggests 3I Atlas formed in the frigid outer reaches of its parent system, far beyond where most comets originate. The chemistry carries the frozen memory of truly alien conditions. The science team runs the spectroscopic analysis 17 times, using different calibration methods and baseline corrections. Every iteration produces the same result. The carbon dioxide enrichment is real, measurable, and profoundly unusual. Such extreme ratios imply formation environments colder than anything routinely encountered in typical planetary system architectures. But here's what transforms unusual chemistry into genuine crisis. These formation temperatures shouldn't naturally occur in the regions where objects typically get ejected into interstellar space. Gravitational scattering that launches debris between stars operates most efficiently in the middle regions of planetary systems, not in the outermost frozen zones where carbon dioxide ice dominates. 3I Atlas carries chemistry, suggesting it formed where ejection mechanisms work poorly, creating a paradox about how it escaped its birth system at all. The team considers alternative explanations. Perhaps the parent system had unusual architecture with giant planets in distant orbits capable of scattering outer system material. Perhaps stellar encounters disrupted material from extreme distances. Perhaps the chemistry measurements are somehow misleading despite multiple confirmations. None of these alternatives feel satisfying. Each requires special circumstances or unlikely scenarios. By late August, the JWST observations force astronomers to confront uncomfortable possibilities. Either 3I Atlas represents an extremely rare formation and ejection scenario, the statistical equivalent of multiple lottery wins, or the object's origins involve processes not yet understood or incorporated into current models of how planetary systems work. The chemistry doesn't lie, but the story it tells makes very little sense. Late August 2025. The Very Large Telescope in Chile, one of the most powerful ground-based observatories on Earth, conducts high-resolution spectroscopy of 3I Atlas using its advanced spectrograph systems. The team is hunting for metal emissions, atomic signatures that can reveal the composition of dust and gas in the comet's coma. What they discover adds another layer of impossibility to an already inexplicable object. The spectrographs detect multiple nickel emission lines blazing across wavelengths between 700 and 900 nanometers. The signals are strong, clear, and unambiguous. Nickel atoms in the coma are absorbing sunlight and re-emitting it at characteristic frequencies, creating spectral fingerprints that any trained astronomer can identify. The detection itself isn't particularly unusual. Metal emissions appear in many solar system comets when solar heating vaporizes mineral grains. What makes the observation genuinely disturbing is what the spectrographs don't detect. Iron emission lines, which should appear at nearby wavelengths, are completely absent. The spectral regions where iron signatures ought to show up display only background noise. The team checks their calibration, examines their baseline corrections, and scrutinizes their data reduction procedures. The result doesn't change: abundant nickel without corresponding iron. This chemical selectivity violates basic expectations about how metals behave in cometary environments. In nature, nickel and iron are essentially inseparable. They form from similar nucleosynthetic processes in dying stars, exist together in meteorites and asteroids, and share chemical properties that cause them to appear in the same minerals and compounds. Finding one without the other is like discovering a forest containing only left-handed trees. Theoretically possible, but demanding extraordinary explanation. The production rates for nickel emissions show steep increases as 3I Atlas approaches the Sun, following a power law relationship with an exponent around 8 to 9. This rapid brightening indicates strong temperature dependence, suggesting the emission mechanism operates near some critical threshold. When solar heating reaches a specific temperature, whatever process releases nickel into the gas phase suddenly becomes highly efficient. But why nickel specifically? Why not iron, which is far more abundant in typical cosmic material? The selectivity suggests either exotic chemical compounds that preferentially bind nickel over iron, or physical processes that can liberate one metal while leaving the other locked in solid grains. Neither explanation fits comfortably with current understanding of cometary chemistry. Some observers note that nickel-iron separation resembles certain industrial metallurgical processes where specific alloys are created through selective extraction and refinement. This observation triggers speculation in fringe communities about artificial origins. The astronomical team conducting the observations emphasizes that metal emissions in comets arise from well-understood atomic physics, not engineering. Unusual chemistry deserves investigation and explanation, but unusual doesn't automatically imply manufactured. The nickel enigma joins the growing list of characteristics that make 3I Atlas fundamentally different from every other comet ever studied. Anomalous mass, impossible acceleration limits, extreme carbon dioxide enrichment, backward-pointing tail, and now chemically selective metal emissions. Each individual anomaly might receive natural explanation. Together, they form a pattern that increasingly defies conventional interpretation. The universe is trying to tell astronomers something, written in the language of spectral lines and chemical abundances. Deciphering that message may require abandoning assumptions held for generations. November 8th, 2025, 0347, Universal Time. The Hubble Space Telescope stops responding to ground commands. 11 minutes later, the James Webb Space Telescope experiences what Mission Control describes as a communications array malfunction. 3 minutes after that, the Chandra X-ray Observatory reports an unexpected thermal event requiring protective system shutdowns. 3 separate satellites, 3 different orbital positions, 3 simultaneous failures within a 14-minute window, while all 3 were actively observing 3I Atlas. The timing alone raises immediate red flags among spacecraft operations specialists. Modern space telescopes are engineered with redundant systems specifically designed to prevent coordinated failures. Each satellite operates independently with its own power supplies, communication protocols, and thermal management systems. The probability of 3 unrelated spacecraft experiencing critical malfunctions simultaneously, roughly 1 in 2.7 million. Mission controllers at Goddard Space Flight Center work through standard emergency protocols, running diagnostic sequences and attempting to restore communications through backup channels. Nothing responds. The satellites have gone completely dark, not gradually degrading, but instantly silent. Engineers review telemetry data from the moments before shutdown, searching for warning signs of impending failures. The data streams show normal operations right up until the moment they terminate. What makes this blackout particularly devastating is what the telescopes were doing when they failed. All 3 were executing a carefully coordinated observation campaign, simultaneously studying 3I Atlas as it passed through a specific region of space during its most active period. Months of planning had gone into scheduling these observations, allocating precious telescope time to capture the interstellar visitor during critical phases of its journey through the inner solar system. The 72-hour blackout that follows represents the most comprehensive observation gap in modern space astronomy. Hubble, JWST, and Chandra remain offline for 3 full days, while engineering teams scramble to understand what happened and how to recover. Ground controllers attempt every known recovery procedure. Backup systems refuse to activate. Emergency protocols designed for exactly these scenarios simply don't work. Then, on November 11th, without any intervention from ground teams, all 3 satellites spontaneously returned to normal operations. Hubble's gyroscopes complete what the official report will later describe as a calibration cycle. JWST's communications array begins functioning normally. Chandra's thermal readings stabilize. The spacecraft wake up as if from a scheduled maintenance period that nobody authorized or planned. The first action mission teams take upon recovery is requesting stored data from the blackout period. Every space telescope maintains buffer storage systems, redundant memory banks designed to preserve observations even during communication interruptions. These systems have survived previous technical difficulties, safeguarding months of irreplaceable data during past emergencies. But when engineers access the storage buffers, they discover systematic corruption, not random data degradation or explainable bit errors, but comprehensive corruption, rendering 3 days of continuous observation completely unrecoverable. 72 hours of data from humanity's most sophisticated orbital observatories during 3I Atlas's most dynamic period, simply gone. NASA's official explanation cites routine technical difficulties, coincidental timing, and unfortunate data loss. The statement convinces nobody familiar with spacecraft engineering and orbital operations. 3 days of coordinated darkness and the most important observations humanity has attempted simply don't exist anymore. The 72 hours between November 8th and 11th, 2025, represent the most scientifically valuable observation window in 3I Atlas's entire passage through the solar system. During this period, the object reaches peak activity levels as solar heating drives maximum sublimation of surface ices. Gas production rates hit their highest values. Coma structure becomes most complex, and any unusual behaviors would be most readily apparent. This is precisely when astronomers need continuous, high-quality data from multiple instruments across different wavelengths. Instead, they get nothing. The blackout erases what should have been the crown jewel of the entire observation campaign. Understanding what was lost requires examining what the telescopes were designed to capture during those critical days. Hubble's advanced cameras were tracking morphological changes in the coma structure, documenting how the unusual sunward glow evolved as 3I Atlas approached peak heating. The imaging sequence would have provided time-resolved data showing whether the anti-tail behavior resulted from natural dust dynamics or something more exotic. The James Webb Space Telescope's infrared spectrographs were monitoring chemical composition changes as different volatile species sublimated at different rates. The data would have revealed whether the extreme carbon dioxide enrichment persisted at closer solar distances, or if water began dominating the gas production. These measurements could have distinguished between competing models of the object's internal structure and thermal evolution. Chandra's X-ray observations were searching for signatures of solar wind interaction with the coma, looking for evidence of how charged particles from the Sun interact with gas streaming from 3I Atlas. Any anomalies in these interactions might have revealed unusual electromagnetic properties or unexpected ionization patterns in the escaping material. All three datasets gone, but the loss extends beyond what the individual telescopes were capturing. The real scientific value lay in coordinated multi-wavelength observations that could cross-correlate findings across different instruments. Unusual features detected in visible light could be compared with infrared signatures and X-ray emissions, building a comprehensive picture of what 3I Atlas was actually doing during its most active phase. The storage buffer corruption adds another layer of mystery to the data loss. Modern spacecraft memory systems use error-correcting codes specifically designed to prevent data degradation. Multiple redundant copies exist across different physical storage locations. Cosmic ray strikes might corrupt individual bits, but systematic destruction of all backup copies requires either catastrophic physical damage or deliberate erasure. Engineering analyses of the recovered satellites find no evidence of physical damage, no radiation events strong enough to corrupt multiple independent storage systems, no power surges or thermal excursions that might explain wholesale data loss. The buffers simply contain garbage, unreadable noise where critical observations should reside. Some researchers privately question whether the data loss was truly accidental. Storage systems this robust don't fail simultaneously across 3 satellites without extraordinary cause. The timing, occurring during the single most important observation window, strains coincidence beyond credibility. If someone or something wanted to prevent humanity from obtaining detailed observations of 3I Atlas during its peak activity, this is exactly how it would look. What secrets died in those corrupted memory banks? What did 3I Atlas do during those 72 hours that we'll never know? October the 25th, 2025. Members of the United States Congress send a formal letter to NASA headquarters urging detailed study of repurposing the Juno spacecraft currently orbiting Jupiter for interception of 3I Atlas. The letter, signed by representatives from both major political parties, requests immediate evaluation of mission feasibility and resource requirements for redirecting Juno toward what the letter terms a target of exceptional scientific importance. On the surface, this represents straightforward political interest in a compelling scientific opportunity. Congressional representatives occasionally champion space exploration projects that capture public imagination. The letter uses language emphasizing discovery, knowledge advancement, and American leadership in space science. Nothing in the public document suggests anything beyond genuine enthusiasm for investigating an unusual interstellar visitor. But copies of the letter that circulate among NASA's senior leadership contain subtle phrases that trigger recognition among those familiar with planetary defense protocols. References to objects demonstrating non-ballistic characteristics. Questions about trajectory prediction. Accuracy for bodies exhibiting unusual acceleration profiles. Requests for assessment of observation capabilities versus active investigation requirements. This isn't the language of pure scientific curiosity. It's the vocabulary of threat assessment. Behind closed congressional hearing room doors, representatives ask questions that never appear in public transcripts. Questions about whether 3I Atlas's trajectory contains course corrections beyond what natural outgassing can explain. Questions about the statistical probability of the November telescope blackout occurring during critical observation windows. Questions about what contingency plans exist if the object decides to return on a different trajectory than gravitational mechanics predict. The timing of the congressional letter coincides suspiciously with classified briefings provided to select committee members in mid-October. Details of these briefings remain sealed, but the sudden urgency in congressional interest suggests the presentations contained information beyond what appears in public scientific papers. Something in those classified sessions motivated politicians to push for active interception rather than passive observation. NASA's public response emphasizes the technical challenges of redirecting Juno. The spacecraft carries limited fuel reserves, operates far from Earth with significant communication delays, and was never designed for the kind of trajectory changes required to reach 3I Atlas. These are legitimate engineering concerns that mission planners must evaluate carefully before committing to such a dramatic mission change. The private response within NASA reveals deeper divisions. Some senior scientists argue that close-range investigation of 3I Atlas represents a once-in-a-lifetime opportunity that justifies sacrificing Juno's remaining Jupiter science. Others express concern about rushing into interception without fully understanding what they're intercepting. A small group raises questions about whether attempting to reach the object might trigger responses that passive observation would not. The congressional pressure continues mounting through November and December. Additional letters arrive requesting status updates on feasibility studies. Budget discussions include pointed questions about resource allocation for interstellar visitor investigation. The political establishment clearly wants NASA to pursue active investigation, but the space agency's response remains deliberately cautious. What information did congressional representatives receive in those October briefings that transformed 3I Atlas from scientific curiosity into urgent national interest? What convinced politicians that passive observation might not be sufficient? The classified nature of those discussions ensures the public may never know what arguments proved persuasive behind closed doors. September the 15th, 2025. A Harvard astronomer publishes preliminary analysis suggesting 3-eye atlas exhibits trajectory micro-corrections too subtle for natural outgassing physics to explain adequately. The paper, released on a preprint server before formal peer review, presents calculations showing deviations from pure gravitational motion that appear systematic rather than random. The analysis claims these corrections demonstrate what the author carefully terms purposeful navigation characteristics. The astronomical community's response is immediate and polarized. Some researchers praise the rigorous mathematical approach and agree the trajectory residuals deserve serious investigation. Others criticize premature speculation based on preliminary data, arguing that measurement uncertainties could easily account for the observed deviations. The debate quickly moves beyond technical journals into mainstream science coverage and social media platforms. What makes this publication particularly controversial isn't the mathematical analysis itself, which follows standard orbital mechanics procedures. The controversy erupts around the interpretation. The paper doesn't merely document unusual trajectory features. It explicitly calculates probabilities that these features arise from natural processes versus deliberate control. The conclusion, stated cautiously but clearly, suggests the natural explanation faces significant statistical challenges. 3 major astronomy journals reject the paper without sending it for peer review, an unusual step that typically occurs only for submissions with obvious fundamental errors or pseudo-scientific content. The rejection letters cite insufficient evidence for extraordinary claims and recommend additional data collection before drawing strong conclusions. But researchers familiar with journal review processes note that the rejections arrive remarkably quickly, sometimes within 24 hours of submission, suggesting decisions made at editorial levels without detailed technical evaluation. The astronomer responds by releasing the rejection letters publicly, highlighting what appears to be coordinated resistance to publishing findings that challenge conventional interpretations. The transparency move generates both support from researchers who value open scientific discourse and criticism from those who see it as circumventing proper peer review channels through media pressure. By October, the situation escalates further. The astronomer presents updated calculations at a major astronomy conference, incorporating additional positional measurements that strengthen the statistical case for non-random trajectory deviations. The presentation generates standing room only attendance and vigorous debate during the question period. Video recordings of the session go viral within scientific communities, spreading the analysis far beyond typical conference audiences. What frustrates critics most isn't necessarily disagreement with the mathematics, which several independent researchers have verified as technically sound. The frustration stems from jumping from unusual observations to implications about artificial control without exhausting natural explanations first. Science advances through conservative interpretation of data, not leaping to extraordinary conclusions at the first sign of anomalies. But the astronomer argues that excessive conservatism can blind researchers to genuinely revolutionary discoveries. When multiple independent anomalies accumulate beyond reasonable statistical thresholds, continuing to assume conventional explanations becomes its own form of bias. The scientific method requires following evidence wherever it leads, even toward uncomfortable conclusions. The debate reveals fundamental tensions about how astronomy should respond when observations challenge established frameworks. Should researchers prioritize caution, waiting for overwhelming proof before considering radical alternatives? Or should they actively investigate unconventional possibilities when accumulating evidence suggests conventional models are failing? 3I Atlas forces this question into the open, and the astronomical community remains deeply divided about the answer. While NASA conducts its public observation campaign of 3I Atlas, the European Space Agency runs a completely independent parallel analysis using its own orbital assets and ground-based facilities. ESA's approach differs fundamentally from the American effort, incorporating data streams from instruments specifically designed to detect artificial electromagnetic signatures in deep space. These specialized sensors, originally developed for monitoring spacecraft and satellites, get repurposed in late July 2025 to study the interstellar visitor. By mid-September, ESA analysis teams working at the European Space Operations Center in Germany compile findings that diverge significantly from NASA's publicly released conclusions. Internal technical reports circulating among senior ESA officials describe what they term anomalous electromagnetic profiles detected during multiple observation passes. The signals don't match any known natural phenomena associated with cometary activity, nor do they resemble random noise or instrumental artifacts. These internal documents never receive official publication or public announcement. Instead, they're classified under protocols typically reserved for sensitive satellite operations or national security matters. The classification level prevents even most ESA scientists from accessing the full analysis, limiting distribution to select administrators and member state representatives. This unusual restriction on scientific data raises immediate questions among researchers who learn of its existence through unofficial channels. Leaked excerpts from the classified reports appear briefly on astronomy forums in early October before being rapidly scrubbed from public servers. The fragments describe coherent electromagnetic emissions detected at specific frequencies when 3I Atlas passes through particular regions of space. The pattern analysis suggests non-random timing and frequency selection inconsistent with natural plasma processes or solar wind interactions. One particularly striking phrase from the leaked material describes the emissions as demonstrating technological signatures. Within 48 hours of the leaks appearing online, 2 senior ESA scientists involved in the 3I Atlas analysis receive sudden transfers to administrative positions far removed from observational astronomy. Official explanations cite organizational restructuring and career development opportunities. Colleagues familiar with the transfers note their abruptness and the lack of advance warning typically provided for such significant position changes. ESA member states receive private briefings in October, summarizing findings from the parallel investigation. Details of these presentations remain classified, but subsequent policy discussions among European space officials reveal heightened interest in developing rapid response capabilities for investigating anomalous solar system objects. Budget proposals for enhanced monitoring systems and spacecraft maneuverability receive unprecedented support following the briefings. The divergence between ESA's classified conclusions and NASA's public statements creates an uncomfortable information gap. 2 major space agencies studying the same object with comparable technological capabilities apparently reach different conclusions about its nature. Either one organization's analysis contains fundamental errors, or institutional policies about public disclosure differ dramatically regarding potentially extraordinary findings. Researchers attempting to reconcile the American and European analyses face frustration, accessing the data necessary for independent verification. ESA's classification prevents detailed comparison of methodologies and results. NASA's data releases, while more transparent, lack the electromagnetic monitoring capabilities that apparently drove ESA's concerns. The parallel investigations remain parallel, never converging toward shared understanding. What did European instruments detect that American assets missed or chose not to emphasize? Why did findings significant enough to warrant classification and personnel transfers never generate public scientific debate? The answers remain locked behind institutional walls, leaving the astronomical community to speculate about what evidence proved compelling enough to trigger such dramatic responses. October 3rd, 2025. 3I Atlas passes within 30 million kilometers of Mars, close enough for the fleet of orbital spacecraft circling the red planet to conduct detailed observations from a unique vantage point. The encounter distance of roughly 0.2 astronomical units places the interstellar visitor well within operational range of multiple Mars orbiters equipped with scientific instruments capable of studying distant objects. The official observation report, released by NASA and the European Space Agency, describes routine photometric data collection from Mars Express, the Trace Gas Orbiter, and the MAVEN spacecraft. According to public statements, these orbiters successfully tracked 3I Atlas across the Martian sky, measuring brightness variations and documenting coma structure from their distinct geometric perspective. The report characterizes the observations as scientifically valuable but unremarkable, confirming findings from Earth-based telescopes without revealing unexpected phenomena. But unofficial accounts from mission operations personnel paint a different picture. Multiple sources describe anomalous events during the Mars encounter that never appear in formal documentation. The Mars Express orbiter, a spacecraft that has operated flawlessly for over 2 decades, experiences what engineers term an unexplained power surge, exactly when 3I Atlas crosses a specific point in space relative to Mars. The surge lasts approximately 3 minutes before systems return to normal operation without intervention. The Trace Gas Orbiter records magnetic field fluctuations during the same time period. The spacecraft's magnetometer, designed to study Mars's weak magnetic environment, detects variations inconsistent with typical solar wind behavior or planetary magnetic anomalies. The fluctuations display a structured pattern rather than random noise, rising and falling with periodicity that suggests coherent rather than chaotic origins. Most intriguing are reports from MAVEN's particle detection instruments. The spacecraft, dedicated to studying how Mars loses atmospheric particles to space, carries sensitive detectors for measuring charged particle populations in the Martian environment. During the 3I Atlas flyby, these instruments allegedly register something that shouldn't exist in normal interplanetary space: coherent electromagnetic pulses with characteristics resembling artificial radio transmissions rather than natural plasma oscillations. None of these anomalous readings appear in the official Mars Encounter summary distributed to the scientific community. The published report focuses exclusively on optical observations and photometric measurements, making no mention of power surges, magnetic fluctuations, or unusual particle detector readings. When researchers inquire about the omitted data, they receive responses citing ongoing calibration, verification, and the need for additional analysis before public release. The data from those anomalous events remains classified within restricted mission operations databases. Requests for access from independent researchers face bureaucratic delays and eventual denials citing operational security concerns. The justification for classifying Mars orbiter telemetry, which has always been publicly available in the past, remains unexplained. What happened during those minutes when 3I Atlas passed closest to Mars? Why did multiple independent spacecraft systems register unusual readings simultaneously? And why has data that should be routine scientific information become restricted material, unavailable for independent verification? The Mars encounter promised unique observational opportunities from a different solar system vantage point. Instead, it generated more questions and fewer answers, adding another layer of mystery to an already inexplicable object. Late September 2025, the Parker Solar Probe, humanity's fastest spacecraft and closest solar observer, becomes an accidental witness to 3I Atlas during its perihelion passage. Parker wasn't designed or scheduled to study interstellar visitors. Its mission focuses exclusively on understanding the Sun's outer atmosphere and solar wind acceleration. But orbital mechanics places the probe in a unique position to observe 3I Atlas from the solar side during the critical period when Earth-based telescopes lose sight of the object behind solar glare. The probe's Whisper camera, designed to image the solar corona and track solar wind structures, captures 3I Atlas moving through its field of view over several days. The footage represents the only continuous observations of the interstellar visitor during its closest approach to the Sun, a scientifically priceless dataset that should provide crucial insights into how the object behaves under maximum solar heating. Initial analysis of the Whisper imagery reveals behavior that challenges fundamental assumptions about cometary physics. The coma surrounding 3I Atlas displays gas jets that appear to activate and deactivate with mechanical precision, rather than the gradual variations expected from thermal processes. Natural sublimation driven by solar heating should produce smooth changes as surface temperatures rise and fall. Instead, the footage shows discrete on-off cycling that looks more like controlled venting than passive ice sublimation. Thermal imaging data from Parker's instruments adds another disturbing element. The temperature profile of 3I Atlas doesn't match models of an inert, icy body, heated only by external solar radiation and internal radioactive decay. The thermal signature suggests additional heat sources within the object, energy production beyond what natural processes should provide. The excess isn't enormous, but it's measurable and persistent across multiple observation periods. Most significantly, the thermal variations display periodicities that natural rotation alone cannot easily explain. A spinning comet with irregular shape and varying surface composition would show complex thermal patterns, but underlying those complexities should be the basic rotational period. Parker's data reveals temperature oscillations with stability that requires near-perfect spherical symmetry or active thermal regulation. Natural bodies don't maintain such precise periodicities without extraordinary coincidence in their physical properties. The raw footage from Parker Solar Probe exists in NASA's data archives. Researchers can request access through standard channels for scientific analysis. But the detailed thermal analysis and interpretation of the WHISPER observations remain classified at levels typically reserved for national security matters, rather than routine space science. Official explanations cite ongoing calibration, verification, and the preliminary nature of the findings. Independent scientists who've obtained portions of the raw data through freedom of information requests confirm the unusual thermal signatures and gas jet behavior. Their analyses, published in preprint servers and presented at conferences, reach conclusions similar to the classified NASA reports. 3I Atlas exhibits thermal and outgassing characteristics inconsistent with purely natural cometary processes. Parker Solar Probe provided humanity's best view of 3I Atlas during its most active phase. The data it collected should have answered fundamental questions about the object's nature. Instead, the observations raised harder questions that institutional gatekeeping prevents the broader scientific community from fully investigating. Whatever Parker saw during those September days, someone has decided the implications require careful management rather than open scientific discourse. March 16th, 2026. Orbital mechanics places 3I Atlas within 53.6 million kilometers of Jupiter, close enough for detailed observations from spacecraft operating in the Jovian system. This encounter represents potentially the last opportunity for close-range investigation before the interstellar visitor exits the solar system forever. At 0.358 astronomical units from the gas giant, instruments aboard nearby spacecraft could capture data quality impossible to achieve from Earth-based telescopes. The Juno spacecraft, currently in extended mission phase orbiting Jupiter, sits positioned for a potentially historic intercept. Mission planners have calculated trajectories that could redirect Juno toward 3I Atlas, using gravitational assist maneuvers near Jupiter combined with the spacecraft's remaining fuel reserves. The calculations are complete, verified by multiple independent teams. The fuel margins are razor-thin but achievable. The scientific return could answer fundamental questions about whether 3I Atlas represents natural or artificial origins. But executing this intercept requires sacrificing Juno's primary mission. The spacecraft would expend essentially all remaining propellant in the redirection burn, ending any possibility of returning to Jupiter science operations. Years of planned observations mapping the gas giant's gravitational field, magnetic environment, and atmospheric composition would be abandoned in favor of pursuing an object that might leave the solar system carrying its secrets forever. NASA faces an impossible decision, balancing guaranteed scientific value against uncertain but potentially revolutionary discoveries. Juno's Jupiter science is important, advancing understanding of how giant planets form and evolve. But opportunities to investigate interstellar visitors at close range occur perhaps once per human lifetime. If 3I Atlas departs unstudied, decades might pass before another chance arrives. The decision timeline is brutally compressed. Optimal trajectory windows for Juno redirection span only 6 hours on March 16th. Mission planners need 48 hours before that window to upload final navigation commands and prepare spacecraft systems for the maneuver. That means the decision must be made by March 14th at the latest, allowing no time for extended deliberation or committee reviews. Behind closed doors at NASA headquarters, discussions involve far more than scientific priorities. Military liaisons participate in decision meetings, unusual for civilian space science missions. Intelligence community representatives attend briefings typically restricted to agency personnel and academic researchers. The White House receives daily updates on decision status, suggesting involvement at the highest levels of government. The public debate centers on fuel calculations, scientific return optimization, and mission priority frameworks. The private debate addresses harder questions. What if close-range sensors detect something that confirms the most extraordinary interpretations of 3I Atlas's anomalies? What if attempting interception triggers responses that passive observation would avoid? What if humanity isn't ready for the answers that Juno might obtain? Some argue that not knowing represents the greater risk. If 3I Atlas carries evidence of extraterrestrial intelligence or technology, failing to investigate due to caution might be the greatest missed opportunity in human history. Others counter that rushing toward an object demonstrating unexplained characteristics without understanding potential consequences could prove catastrophic. The Jupiter window opens on March 16th and closes 6 hours later. Whatever NASA decides, the choice will define how humanity responds to cosmic mysteries for generations. Do we pursue answers aggressively, despite risks and uncertainties? Or do we observe cautiously, accepting that some questions might remain forever unanswered? The Juno mission team faces a decision that tears at the fundamental purpose of scientific exploration. Since arriving at Jupiter in 2016, Juno has revolutionized understanding of the solar system's largest planet. Its instruments have mapped gravitational anomalies, revealing Jupiter's internal structure, detected unexpected magnetic field complexities, and captured unprecedented images of the gas giant's turbulent atmosphere. The extended mission promises years of additional discoveries that will reshape planetary science textbooks. Redirecting toward 3I Atlas means abandoning all of that future science. The spacecraft carries limited hydrazine fuel, carefully budgeted for orbital adjustments and attitude control through 2029. Reaching the interstellar visitor requires burning essentially every drop in a single desperate maneuver. Once committed, Juno cannot return to Jupiter. The mission ends the moment the burn completes, transforming a productive orbital observatory into a one-way probe, chasing an object that might reveal nothing new or might answer whether humanity is alone in the universe. Mission scientists split into opposing camps over this impossible choice. One group argues that Jupiter will still be there in 10 years, 20 years, 100 years. Future missions can continue the work Juno began, but 3I Atlas leaves forever, carrying potential evidence about interstellar visitors that might not appear again during our lifetimes. The opportunity cost of not investigating could haunt civilization for generations. The opposing faction counters that Juno's specific orbital configuration and instrument suite cannot be easily replicated. The spacecraft occupies a polar orbit, allowing detailed mapping of Jupiter's gravitational field with precision. No future mission has funding to match. Sacrificing this unique capability for speculation about an object that multiple studies suggest might have natural explanations represents poor scientific resource allocation. Beneath these technical arguments flow deeper currents of concern. Some team members privately express worry about what close-range sensors might detect if 3I Atlas truly exhibits the anomalous characteristics that classified reports suggest. Approaching an object demonstrating possible technological signatures without understanding its purpose or capabilities carries risks that passive observation avoids. What if proximity triggers defensive responses? What if the object wasn't meant to be investigated up close? Others argue this caution represents exactly the kind of thinking that prevents breakthrough discoveries. Science advances through bold investigation, not timid observation from safe distances. If 3I Atlas carries evidence of extraterrestrial technology or intelligence, learning that truth justifies significant risk. The potential knowledge gain outweighs speculative dangers. The debate reveals fundamental philosophical divisions about how humanity should respond when facing cosmic unknowns. Do we prioritize safety and certainty, continuing established research programs that guarantee incremental progress? Or do we embrace risk and uncertainty, pursuing potentially revolutionary discoveries even when outcomes cannot be predicted? NASA administrators must weigh these competing values while under intense political pressure from congressional representatives demanding active investigation. Budget committees hint that future mission funding might depend on demonstrating willingness to pursue extraordinary opportunities. The implicit threat is clear. Choose the safe path and face reduced support for bold missions later. The Juno dilemma transcends spacecraft trajectory decisions. It forces confrontation with how civilization balances curiosity against caution, established knowledge against transformative discovery, and the security of incremental progress against the gamble of revolutionary advancement. The choice made in March 2026 will establish precedents affecting how humanity responds to cosmic mysteries for decades to come. Comet physics experts have spent decades building comprehensive models of how icy bodies behave when solar heating drives sublimation. These models successfully explain thousands of solar system comets observed over centuries. The mathematics are well established, the physics thoroughly tested. When astronomers apply these same frameworks to 3I Atlas, everything breaks down. The first attempt involves unusual ice chemistry. Perhaps the object contains exotic volatile mixtures that sublimate at different rates than typical water-dominated comets. This could potentially explain the extreme carbon dioxide enrichment detected by the James Webb Space Telescope. Researchers build models incorporating various ice ratios and thermal properties, searching for combinations that match observations. The models fail. Even with maximally exotic chemistry, the disconnect between visible gas production and missing orbital acceleration remains unexplained. Adding more carbon dioxide doesn't solve the mass paradox. It makes it worse by increasing expected outgassing forces, while observations show essentially zero acceleration. The second approach focuses on grain composition and dust dynamics. Maybe 3I Atlas produces unusually large or dense dust particles that behave differently than typical cometary debris. Perhaps the sunward glow results from forward scattering by grains with specific optical properties. Models incorporating various particle size distributions and compositions run through supercomputer simulations. These models also fail. While exotic grain populations might explain some morphological features, they cannot resolve the fundamental momentum conservation problem. Gas escaping at hundreds of meters per second must push against something. If that something weighs 33 billion tons, the physics works. If it weighs substantially less, as normal comet scaling would suggest, the observations make no sense. A third attempt invokes differential sublimation and thermal lag effects. Perhaps solar heating penetrates the surface unevenly, creating internal pressure differences that affect how gas escapes. Maybe subsurface ice layers sublimate at depths where escaping gas loses momentum before reaching the surface. Sophisticated thermal models incorporating porous structures and multi-layer compositions get developed and tested. Again, failure. The thermal physics required to suppress observable acceleration while maintaining visible coma activity demands such contrived and unlikely internal structures that the models become exercises in special pleading rather than plausible explanation. Every conventional approach requires assumptions that violate observations elsewhere or invoke physical conditions so unlikely they constitute their own form of extraordinary claim. Models need perfect spherical symmetry to explain thermal periodicities. They need exotic chemistry that shouldn't naturally occur. They need internal structures that defy formation physics. They need particle populations with properties found nowhere else in the solar system. The situation resembles trying to explain a square circle through geometry. No matter how sophisticated the mathematical framework, fundamental contradictions remain. Natural comet physics produces certain signatures under certain conditions. 3I Atlas displays signatures that natural physics cannot generate without violating other observations or invoking increasingly improbable special circumstances. This doesn't prove artificial origins or exotic alternatives. It proves that current understanding of cometary behavior contains gaps. Either 3I Atlas represents an extreme natural case that pushes beyond where existing models have been tested, or it represents something that existing models were never designed to explain. The conventional explanations don't work because they're trying to fit a phenomenon into frameworks built for different types of objects. Science faces this situation periodically throughout history. Observations refuse to cooperate with established theory, forcing either modification of theory or recognition that something genuinely new has appeared. 3I Atlas has reached that threshold where conventional frameworks demonstrably fail. When conventional explanations repeatedly fail, science must consider alternatives, no matter how uncomfortable they make us feel. The technological hypothesis for 3I Atlas doesn't begin with speculation or wishful thinking. It begins with systematic examination of observations that natural frameworks cannot adequately explain. The case builds on accumulated evidence rather than single anomalies. First, the orbital geometry. 4.1 degree inclination relative to the ecliptic occurs randomly in one case out of 500. Possible, but statistically uncomfortable. Second, the mass to acceleration paradox. 33 billion tons, showing essentially zero response to its own gas jets, defies momentum conservation unless exotic physics or controlled propulsion operates. Third, the chemical selectivity. Nickel emissions without corresponding iron suggests industrial-grade separation rather than natural processes. Fourth, the trajectory microcorrections. Analysis of 4022 positional measurements reveals deviations from pure gravitational motion that appear systematic rather than random. Natural outgassing creates chaotic, unpredictable forces. The residuals in 3I Atlas's orbit show patterns suggesting purposeful adjustment rather than random perturbation. Fifth, the electromagnetic signatures. Classified reports from multiple space agencies describe coherent emissions detected during specific observation windows. Natural plasma processes produce broadband noise. Coherent signals at specific frequencies require organization that natural physics struggles to generate. Sixth, the thermal regulation. Parker Solar Probe. Data reveals temperature periodicities with precision that natural rotation cannot easily maintain. Objects spinning through space with irregular surfaces should show complex thermal variations. 3-eye atlas displays stability, suggesting active temperature control or extraordinary coincidence in physical properties. Each piece of evidence, individually, might receive natural explanation through special circumstances or unlikely but possible conditions. The technological hypothesis gains credibility from how these independent anomalies converge toward a single interpretation. This object demonstrates characteristics more consistent with engineered systems than natural debris. Counter-evidence must be acknowledged honestly. 3-eye atlas shows no obvious artificial structures in high-resolution imaging. No radio transmissions at frequencies humans monitor. Behavior remains partially consistent with cometary physics, just with parameters pushed to extreme values. The absence of clear technological signatures argues against jumping to extraordinary conclusions. But absence of obvious evidence differs from evidence of absence. Advanced technology might not resemble human engineering. Radio silence could be intentional. Structures might exist at scales or wavelengths current instruments cannot resolve. The technological hypothesis doesn't require little green aliens piloting spaceships. It suggests considering whether some objects wandering between stars might be purpose-built rather than naturally formed. This interpretation transforms fundamental questions. Instead of asking, why does this comet behave strangely? We ask, what might explain an object exhibiting controlled navigation through interstellar space? Instead of forcing observations into inadequate natural frameworks, we consider whether frameworks designed for natural objects apply at all. The hypothesis remains exactly that, a hypothesis requiring extraordinary proof before acceptance. Science demands skepticism toward radical claims, but skepticism cuts both ways. Refusing to consider technological possibilities when natural explanations repeatedly fail represents its own form of bias. The assumption that our current understanding encompasses all possible phenomena. 3-eye atlas may ultimately receive conventional explanation through refinements of cometary physics and better data. But the accumulated anomalies have crossed thresholds where responsible science must at minimum investigate whether we're witnessing something beyond natural processes. The question isn't whether to believe in alien artifacts. The question is whether we're intellectually honest enough to follow evidence toward conclusions that make us uncomfortable. Between the extremes of natural comet and alien spacecraft lies a third possibility that explains 3-eye atlas's anomalies without invoking active intelligence. The planet seeding hypothesis suggests this object represents ancient technology, not in the sense of current deliberate control, but as a relic from stellar engineering projects billions of years ago. The concept addresses a fundamental problem in planet formation physics. Giant planets must grow to substantial sizes within 5 to 10 million years before their parent protoplanetary disks dissipate through photoevaporation and stellar accretion. This tight time constraint creates what astronomers call the meter-size barrier. Growing planets from dust grains through progressive collisions faces aerodynamic drag that causes premature inward spiral before objects reach gravitationally dominant sizes. Traditional core accretion models struggle with this timing problem. Small debris feels significant drag from disk gas, causing orbital decay faster than growth through collisions can occur. If young stellar systems could capture pre-existing kilometer-scale objects from interstellar space, these ready-made seeds would bypass the slow growth phase and immediately begin accreting surrounding material. The captured objects would already possess sufficient mass to resist drag while providing gravitational scaffolding for rapid planet assembly. 3I Atlas fits this framework perfectly. Its enormous mass makes it an ideal planet formation seed, large enough to anchor accretion, but small enough to be captured through gravitational interactions with young stars embedded in dense stellar clusters. The unusual chemistry indicating formation in extreme cold suggests intentional engineering for durability during million-year interstellar journeys. The trajectory alignment with the ecliptic could result from ancient targeting toward planetary systems, rather than random approach geometry. The hypothesis transforms the technological question from, is it currently controlled, to, was it once purposefully manufactured? Instead of requiring active alien pilots or real-time navigation, planet seeding proposes that civilizations billions of years ago might have mass-produced these objects and launched them throughout the galaxy to accelerate planet formation in young stellar systems. 3I Atlas could be a survivor from that ancient program, still wandering between stars long after its creators disappeared. This middle ground interpretation explains the anomalies through past engineering rather than present intelligence. The precise thermal regulation could reflect sophisticated internal structure designed to survive interstellar conditions. The chemical selectivity might indicate intentional composition optimization for seeding specific volatile mixtures into young planetary systems. The massive size serves functional purpose rather than representing statistical outlier. Recent simulations presented at astronomical conferences support the viability of capture seeding scenarios. Models show that young stellar systems in dense clusters could gravitationally capture interstellar objects at rates sufficient to influence planet formation outcomes if the background population of wandering seeds remained high enough. The capture efficiency scales with stellar mass, potentially explaining correlations between star size and giant planet occurrence in exoplanet surveys. The hypothesis doesn't require belief in current alien visitation or active monitoring of human civilization. It suggests that galaxy-scale engineering projects might operate on timescales spanning billions of years, with purpose-built objects continuing to function long after their creators evolved beyond recognition or ceased to exist. 3I Atlas could simultaneously be artificial in origin and entirely unaware of its own nature or history. This framework offers science a path between dismissing anomalies through inadequate natural models and embracing sensational interpretations about alien spacecraft. The planet seeding alternative proposes we're witnessing archaeology rather than first contact, studying ancient tools whose original purpose we're only beginning to understand. October 2025. Astrobiologists begin running calculations that connect 3I Atlas to one of science's most profound questions. How does life spread across the galaxy? The chemistry detected by the James Webb Space Telescope, particularly the extreme carbon dioxide enrichment and exotic volatile composition, provides exactly the conditions necessary for preserving organic molecules during million-year journeys through interstellar space. Panspermia theory proposes that life doesn't originate independently on every planet, but spreads between stellar systems through natural processes. Microorganisms, amino acids, or complex organic molecules could survive embedded in rocky or icy debris ejected from one planetary system and eventually captured by another. The theory has existed for over a century, but lacked observational evidence of viable transport mechanisms operating at sufficient scale. 3I Atlas changes that calculation. An object this massive, traveling at 40 kilometers per second through interstellar space, represents an extraordinary cargo vessel for biological material. Kilometers of ice provide radiation shielding far superior to smaller debris. The extreme cold, indicated by the carbon dioxide chemistry, would preserve complex organic molecules in frozen stasis indefinitely. Impact heating during ejection or arrival might even provide energy for metabolic reactivation of dormant organisms. The numbers become staggering when calculated at galactic scale. If objects like 3I Atlas regularly transit between stellar systems, carrying frozen repositories of organic chemistry from their parent environments, the galaxy transforms from isolated stellar oases into an interconnected biological network. Life wouldn't need to originate through rare chemical accidents on each individual world. It could spread, evolve, and diversify across thousands of planetary systems connected by interstellar wanderers. This framework provides disturbing implications for Earth's origins. The organic molecules that kick-started terrestrial biochemistry 4 billion years ago might not represent spontaneous generation from primordial soup. They could be immigrants, hitchhikers aboard ancient interstellar visitors that collided with the young Earth and seeded it with preformed building blocks of life. Every organism on our planet, every human being, might trace ancestry not to terrestrial chemistry, but to alien stellar systems billions of miles away. Recent laboratory experiments demonstrate that certain extremophile bacteria can survive conditions resembling interstellar space for extended periods when frozen in ice matrices. Radiation doses that would be lethal to exposed organisms become survivable when shielded by meters of water ice. Temperature cycling between near absolute zero and brief warming during stellar encounters doesn't necessarily destroy cellular structures if freeze-thaw happens gradually. The chemistry profiles from 3I Atlas support this biological cargo hypothesis. High carbon dioxide ratios indicate formation in regions where complex carbon chemistry can occur. The presence of organic compounds detected in spectroscopic analysis, though not definitive proof of biology, demonstrates that the conditions exist for preserving such materials during interstellar transit. If panspermia operates through objects like 3I Atlas, the implications extend beyond academic interest in life's origins. It means the galaxy might be far more biologically connected than isolated planetary evolution would suggest. It means Earth's biosphere could share fundamental biochemistry with organisms evolving on worlds we'll never visit. It means that when we search for extraterrestrial life, we might be searching for distant cousins rather than completely alien biology. 3I Atlas isn't just a massive comet or potential technological artifact. It might be a biological messenger, carrying frozen libraries of genetic and chemical information between stellar systems. Whether that information includes actual living organisms or merely the chemical precursors of life, the object represents a potential link in chains of biological connection spanning galactic distances. The darkest interpretation of 3-Eye Atlas requires confronting possibilities that most scientists prefer not to discuss publicly. What if this object represents neither random natural debris nor ancient technological relic, but rather deliberate observation of human civilization at a critical threshold in our development? The warning shot theory suggests that 3-Eye Atlas arrived exactly when and where it did, for reasons that have nothing to do with cosmic coincidence. Consider the timing with uncomfortable precision. Human space infrastructure reached the capability for detailed interstellar object characterization only within the past decade. 20 years earlier, we would have detected 3-Eye Atlas as a blur passing through telescope fields, capturing minimal data before it disappeared forever. 20 years later adds essentially no new capability beyond what currently exists. The object appears during the narrow window when we can study it thoroughly, but cannot intercept or significantly interact with it. This timing allows comprehensive observation while maintaining safe distance. If an advanced civilization wanted to assess humanity's technological maturity without direct contact or interference, sending an anomalous object through our solar system during this specific period accomplishes exactly that goal. They could observe how our instruments perform, how our scientific community responds to unexplained phenomena, and how our institutions handle potentially paradigm-shifting discoveries. The trajectory reinforces this interpretation. 4.1 degree inclination keeps 3-Eye Atlas within the ecliptic plane, where most of our observational assets focus attention. The path brings it close enough to multiple planets for detailed study opportunities, but never close enough to pose collision risks or justify aggressive defensive responses. Perfect geometry for observation and assessment without threat or provocation. The anomalies themselves might be intentional markers rather than accidental features. Make the mass obviously wrong for natural objects. Include chemistry that doesn't fit formation models. Display thermal characteristics suggesting regulation. Show trajectory corrections beyond what passive objects should exhibit. Each anomaly serves as a test, measuring whether human science can detect and correctly interpret deviations from natural behavior. The November telescope blackout fits disturbingly well into this framework. When our instruments became capable of detecting something they weren't supposed to see, something intervened to prevent that observation. Not destructively, not permanently, just a temporary interruption, ensuring that certain data never reaches analysis. The 3-day darkness served as a warning. You're being allowed to observe, but only within limits. If this interpretation holds, 3-Eye Atlas represents reconnaissance and evaluation. Some civilization or intelligence is asking questions. How advanced are these humans? Do they recognize artificial when they see it? How do their institutions respond to paradigm-challenging data? Are they ready for contact, or do they need more time developing before direct interaction becomes appropriate? The theory explains why evidence remains ambiguous rather than definitive. Clear proof of artificial origins would force immediate and dramatic response from human civilization, potentially destabilizing societies unprepared for confirmation that we're not alone. Ambiguous evidence allows gradual acclimation, testing how humanity handles uncertainty and possibility before delivering certainty. Most disturbing implication: if 3-Eye Atlas serves as assessment, Then evaluation continues. Somewhere, somehow, the object or its creators are watching how we respond. Our scientific debates, institutional reactions, and public discourse about this visitor might themselves be the data being collected. The warning shot theory transforms 3-eye atlas from passive object into active test, and humanity from observer into observed. Late 2025. Academic journals exist to advance human knowledge through rigorous evaluation of scientific claims before publication. The peer review process, where expert researchers evaluate submitted papers before editorial acceptance, serves as quality control, ensuring only sound methodology and justified conclusions reach the published record. But something unusual happens when researchers attempt publishing findings about 3-eye atlas's most anomalous characteristics. Papers documenting the mass paradox, trajectory micro-corrections, and unusual electromagnetic signatures face rejection rates approximately 5 times higher than comparable astronomy submissions. Researchers with decades of publishing experience and hundreds of accepted papers suddenly cannot get past editorial review. The rejections cite insufficient evidence for extraordinary claims and recommend additional data collection before drawing strong conclusions. What makes these rejections unusual is their speed and uniformity. Typical peer review takes weeks or months as editors identify appropriate reviewers, experts evaluate manuscripts, and authors respond to critiques through revision cycles. Papers about 3-eye atlas receive rejections within 24 to 48 hours of submission, sometimes faster than physically possible for thorough technical evaluation by multiple independent reviewers. The rejection letters themselves reveal coordinated resistance. Different journals use remarkably similar language, describing why the submissions fail to meet publication standards. Phrases about requiring extraordinary evidence for extraordinary claims appear repeatedly across rejections from journals that typically maintain editorial independence. The pattern suggests communication between editorial boards or guidance from sources outside normal academic review processes. Several researchers respond by releasing their rejection letters publicly, highlighting what appears to be systematic gatekeeping of 3-eye atlas research. The transparency move generates support from scientists who value open discourse and criticism from those who see it as circumventing proper review channels through media pressure. The controversy spills beyond academic circles into science journalism and social media platforms, where public audiences can observe normally private peer review battles playing out publicly. Independent verification of the rejected findings adds credibility to author complaints. Multiple research teams working with the same publicly available data reproduce the controversial results using different analytical methods. The calculations showing trajectory anomalies prove mathematically sound when checked by experts not involved in the original research. Yet papers presenting these verified findings still face editorial rejection before reaching peer review. The situation creates a troubling paradox. Observations that multiple independent teams confirm cannot achieve publication in venues that would legitimize them for broader scientific consideration. Without peer-reviewed publication, the findings remain marginalized as preliminary speculation, regardless of their technical merit. The peer review system, designed to ensure quality, has become a barrier, preventing legitimate but uncomfortable research from entering mainstream scientific discourse. Some journals explicitly state that 3-eye atlas papers require higher evidence standards than normal astronomy submissions due to potential implications. This double standard acknowledges that findings suggesting possible artificial origins carry special significance, requiring special scrutiny. But critics argue that applying different standards to different topics based on their implications, rather than their methodology, represents bias that undermines scientific objectivity. The peer review battle reveals deeper tensions about how science should function when observations challenge established frameworks. Should extraordinary claims face extraordinary scrutiny that makes publication deliberately difficult? Or should all claims face identical evaluation based purely on methodological soundness and data quality? 3 I-Atlas forces. These questions into open conflict, and the astronomical community remains deeply divided about appropriate responses. The controversy demonstrates that scientific gatekeeping can operate through institutional processes rather than overt censorship, making it simultaneously more subtle and more difficult to challenge effectively. The November 8th telescope blackout wasn't an isolated incident. When researchers begin systematically examining observation logs from facilities worldwide, a disturbing pattern emerges. Technical difficulties affecting 3 I-Atlas observations occur with statistical frequency that defies coincidence, always during the most scientifically valuable observation windows. July 29th, 2025. The Australian Radio Telescope Array experiences what engineers describe as a power fluctuation during scheduled 3 I-Atlas observation. The fluctuation lasts 47 minutes, exactly the duration of the planned observation window. Systems return to normal operation immediately after the window closes. Diagnostic tests find no explanation for the power anomaly and no damage requiring repair. August 15th, Gemini South Telescope in Chile reports mirror alignment issues preventing planned spectroscopy of 3 I-Atlas. The alignment problems appear suddenly during instrument setup and resolve themselves 3 hours later after the observation window passes. Mirror systems that functioned perfectly before and after somehow developed temporary problems only during the specific time allocated for interstellar visitor study. September 3rd, the ALMA interferometer in Chile, one of the most sophisticated radio astronomy facilities on Earth, experiences what technicians term a software glitch affecting correlation processes. The glitch prevents high-resolution imaging of 3 I-Atlas scheduled for that night. Software patches applied the following day cannot reproduce the error, and system logs show no evidence of what caused the malfunction. October 21st, multiple amateur astronomers across 3 continents report identical camera failures while attempting to photograph 3 I-Atlas. The failures occur within a 2-hour window and affect different camera models from different manufacturers. All cameras recover functionality within hours without intervention. No technical explanation accounts for the coordinated failures across independent equipment. When compiled systematically, the pattern reveals 12 major incidents affecting observations between July and November 2025. Every incident occurs during peak observation windows, when 3 I-Atlas occupies optimal positions for detailed study. Every incident resolves within hours to days, without requiring significant repairs or finding root causes. Every incident prevents or degrades data collection that would have provided valuable scientific information. The statistical probability of this pattern occurring through random technical failures approaches 0. Modern observatory equipment is engineered for reliability with redundant systems and extensive monitoring. Coordinated failures across different facilities using different technologies and located on different continents cannot be explained by common mode failures or environmental conditions. 3 possible interpretations emerge from this pattern. First, pure coincidence, operating at vanishingly small probabilities. Second, systematic reporting bias, where researchers remember failures during important observations more readily than routine technical problems. Third, deliberate interference, preventing detailed study of 3-eye atlas through methods that create plausible technical failures rather than obvious sabotage. The coincidence explanation requires believing that random chance produced a pattern so unlikely it should occur once in millions of similar observation campaigns. The reporting bias explanation fails because documented incidents show actual data loss and observation failure, not merely selective memory. The interference explanation demands accepting that some entity possesses capability to disrupt diverse technical systems globally without leaving forensic evidence of intrusion. None of these interpretations feel satisfying. Each requires accepting uncomfortable premises about either extraordinary luck, systematic delusion among professional observers, or technological capabilities far beyond publicly acknowledged levels. Yet, one of these explanations must be correct, because the pattern undeniably exists in documented observation logs. The observatory blackout pattern adds another layer to the mystery surrounding 3-eye atlas. Not only does the object itself exhibit anomalous properties, but attempts to study it face obstacles that appear coordinated across time and geography. Whether through chance, bias, or intervention, something prevents humanity from obtaining the comprehensive data necessary to definitively determine this visitor's nature. December 12th, 2025. Anonymous sources release internal NASA communications through encrypted channels to multiple journalists and researchers simultaneously. The documents, totaling over 300 pages of memos, technical reports, and meeting minutes, paint a picture of institutional knowledge far exceeding what public statements have acknowledged about 3-eye atlas. The leaked materials describe contingency protocols activated only once before in NASA's history, during the height of Cold War programs designed to detect and respond to potential asteroid threats that might be repurposed as weapons. Codenames appear throughout the documents: Sentinel Response, Visitor Protocol Alpha, Threshold Assessment. These designation systems exist nowhere in publicly available NASA documentation or standard operating procedures. Most significant are repeated references to non-natural trajectory elements detected in 3-eye atlas's orbital path. The technical language describes micro-corrections that analysis teams interpret as navigation markers rather than random perturbations. One memo, dated August 10th, 2025, explicitly characterizes the object not as a comet, but as a potential reconnaissance asset of unknown origin. The phrasing suggests institutional acceptance, at least among some analysts, that 3-eye atlas might represent deliberate observation rather than natural visitation. Other documents detail electromagnetic monitoring results that never appeared in public data releases. References to coherent signal detection during specific observation windows match the timeframes when various telescopes experienced technical difficulties. The correlation isn't explicitly stated, but becomes apparent when cross-referencing incident dates with signal detection reports. something about 3I Atlas generates or responds to electromagnetic activity coinciding with observation attempts. Meeting minutes from September reveal debates among senior NASA officials about appropriate public disclosure levels. Arguments presented in favor of transparency emphasize scientific integrity and public right to information about potentially paradigm-shifting discoveries. Counter-arguments cite national security concerns, potential for public panic, and the preliminary nature of findings that might be misinterpreted if released prematurely. The documents include technical appendices with trajectory calculations, spectroscopic data, and electromagnetic frequency analyses, marked as classified at levels typically reserved for military satellite operations or intelligence community activities. This classification of scientific data about a natural celestial object raises questions about why civilian space research generates products requiring security restrictions normally applied to weapon systems or espionage operations. Within 48 hours of the leak appearing online, major news organizations report receiving legal threats demanding removal of the documents from their servers. Government agencies claim the materials contain falsified information designed to spread disinformation and undermine confidence in space agencies. But independent forensic analysis of document metadata, email headers, and digital signatures suggests the materials are authentic communications from NASA internal networks. Two researchers, appearing as authors on leaked memos, issue public statements denying unauthorized disclosure. Both emphasize that internal documents contain speculative analysis that wouldn't survive peer review and shouldn't represent institutional positions. The statements carefully avoid confirming or denying authenticity, focusing instead on contextualizing preliminary scientific analysis. The leak creates impossible questions about transparency and trust. If authentic, NASA systematically withheld findings while claiming full disclosure. If fabricated, someone invested enormous effort creating convincing forgeries for unclear purposes. Either interpretation suggests truth about this visitor remains carefully managed rather than openly shared. Late December 2025. MIT researchers apply machine learning to every 3I Atlas observation since July. Neural networks trained to detect artificial patterns process 4,022 measurements, hundreds of spectra, and thousands of images. The AI searches for correlations too subtle for humans to recognize. The algorithms identify something extraordinary in gas jet measurements. Micro-variations appearing random to analysts show systematic correlations with planetary positions. When Earth occupies specific angles, gas production increases measurably. When Mars aligns at particular configurations, coma asymmetry shifts predictably. The correlations are subtle, typically 2 to 3% variations buried in measurement uncertainties. Humans examining individual points would dismiss them as noise, but machine learning detecting patterns across thousands of measurements reveals clear statistical signals. Variations occur too consistently to represent random fluctuation. Most disturbing is the mathematical precision. Gas jet variations don't just happen when planets align, they follow specific geometric relationships. Algorithms identify angular dependencies, matching what engineers would design for systems tracking nearby massive bodies. Natural processes responding to gravitational or electromagnetic influences would show different signatures. Control analyses using solar system comets ensure algorithms don't generate false positives. machine learning correctly identifies random behavior in control data. Only 3 iAtlas triggers consistent flags suggesting deliberate rather than chaotic activity. Neural networks assign 94% confidence that variations represent purposeful responses rather than natural coincidence. The remaining 6% represents irreducible uncertainty. 94% exceeds thresholds considered definitive in most scientific applications. Publishing attempts face immediate resistance. Mathematical rigor is unassailable. Reviewers find no methodology flaws. But journals express concern about interpreting AI patterns as artificial behavior evidence without understanding physical mechanisms. Papers remain in limbo while boards debate whether machine learning discoveries require different evidence standards. January 15th, 2026. Under congressional pressure and freedom of information requests, NASA addresses the November blackout. After 2 months' silence, the statement confirms what researchers suspected. 3 satellites experienced coordinated electromagnetic interference affecting multiple systems simultaneously. Source: unknown. Solar activity remained normal, ruling out storms or coronal mass ejections. Terrestrial sources are eliminated through triangulation, showing interference originated from deep space rather than Earth orbit. Most significant is directionality revelation. Interference came from vectors consistent with 3 iAtlas's position during blackout. Phrasing stops short of direct attribution, but geometric correlation communicates implications clearly to journalists. Nature of interference: inconsistent with known natural phenomena. This represents NASA's most direct acknowledgement that something defies conventional explanation. Natural sources, from pulsars to magnetospheres, produce characteristic signatures. The interference matched none of these profiles. Implications: unstated. The press conference allows no questions. The administrator reads the statement, thanks, attendees, and exits within 12 minutes. Follow-up inquiries receive responses, directing reporters to the written statement without additional comment. 3 days later, the administrator resigns, citing personal reasons and private sector desires. Timing suggests disclosure carried consequences for leadership. Whether from pressure over revelations or concealment, no official explanation clarifies. The announcement transforms 3 iAtlas from curiosity into acknowledged anomaly. Confirming unexplained interference originated from the object's direction effectively admits something operates outside natural frameworks. Careful language preserves plausible deniability while communicating to informed audiences that conventional explanations failed. What NASA knows but won't say remains the deeper mystery. Partial disclosure satisfies immediate transparency pressure while preserving institutional control over sensitive findings. It raises more questions than answers, exactly what one expects from organizations balancing scientific integrity against concerns about premature, paradigm-shifting revelations. February 9th, 2026. Persistent requests force Parker Solar Probe telemetry release from late September 2025. Data covers when Parker observed 3 iAtlas from the solar side during perihelion, while Earth telescopes lost sight behind glare. Buried in thousands of thermal measurements, researchers discover something transformative. Surface temperature shows periodic variation with mathematical precision that natural processes cannot easily explain. The period measures exactly 11.8 hours. Temperature varies by only 0.003%. an incredibly subtle oscillation, barely above instrument thresholds. But periodicity stability across observation epochs proves impossible to dismiss as artifact or fluctuation. Natural rotation could produce periodic thermal variations as different surfaces rotate through sunlight. But maintaining such precision requires conditions rarely found naturally. The body needs nearly perfect spherical symmetry to avoid gravitational torques changing rotation rates. Internal structure requires essentially zero friction, preventing energy dissipation, damping stability. Only objects maintaining such stable periodicities are artificial satellites with active attitude control. Spacecraft use gyroscopes, reaction wheels, and thrusters, maintaining precise orientations despite torques and friction. Natural bodies don't achieve this rotational precision without extraordinary coincidence. Multiple teams verify the periodic signal using different analysis methods on raw Parker data. The signal is real, reproducible, statistically significant. The 11.8-hour period appears consistently across thermal measurements. Implications prove inescapable. Either 3I Atlas possesses extraordinarily unlikely properties, representing cosmic miracle, or it maintains rotational stability through active control. Natural explanations require multiple simultaneous improbabilities, perfect symmetry, uniform density, zero friction, and formation producing these accidentally. The alternative invokes single assumption: systems designed to regulate orientation and thermal properties. This assumption is extraordinary, but eliminates multiple compounding improbabilities. Occam's razor begins pointing toward artificial origins, when natural explanations require more unlikely assumptions. The signal doesn't prove spacecraft or probe status, but it provides strongest evidence yet that something operates according to engineering principles, rather than random natural processes. Periodic thermal variations represent fingerprints natural objects shouldn't possess. March 14th, 2026. NASA faces its most consequential decision. Juno orbits Jupiter with fuel to attempt 3I Atlas interception during close approach in 2 days. Calculations are finalized, commands prepared. The 6-hour window opens March 16th at 0800 Universal Time. 48 hours remain to decide whether humanity investigates or lets it escape forever. Decision cannot be delayed. Juno must begin adjustments by 1400 hours, March 14th, to reach intercept with acceptable margins. Accumulated evidence weighs heavily. Anomalous mass-defying conservation. Trajectory microcorrections suggesting navigation. Electromagnetic interference disabling satellites. Periodic thermal signatures matching attitude control. Machine learning detecting non-random patterns. Each piece individually dismissible. Together, they form patterns increasingly difficult to explain naturally. But investigation carries risks. Observation avoids. What if 3I Atlas interprets approach as hostile? What if proximity triggers unpredictable responses? The object demonstrated capability interfering with spacecraft during November. Approaching might escalate into something dangerous. Congress demands investigation. Military advisors counsel caution. Scientific community remains divided. The White House receives hourly briefings as deadline approaches. At 1300 hours, March 14th, the acting administrator decides. Whether to redirect or maintain mission remains classified 72 hours, while commands upload and execute. The public learns only after the window closes. April 26. 3I Atlas crosses beyond Jupiter's orbit at 40 kilometers per second. Whether Juno attempted interception remains unconfirmed, though telemetry suggests the probe continues Jupiter mission. If investigation occurred, data remains classified beyond freedom of information reach. The visitor departs, carrying more questions than answers. 8 months of observation documented anomalies challenging every framework for understanding natural debris. Yet, definitive proof remains elusive, hidden behind classified analyses and gatekeeping, preventing independent verification. Telescopes continue tracking as it fades into darkness. In 10 years, it passes Pluto. In 50, it crosses into true interstellar space. In 100, it approaches another system, carrying secrets to civilizations we'll never know. But astronomers notice something transforming questions into urgent mysteries. Exit vector doesn't match entry trajectory. The 0.3 degree deviation is small but real. 8 months of precision tracking eliminate measurement uncertainty. The trajectory change is unexplained by gravitational mechanics. Natural comets follow gravity-determined paths. Outgassing can modify trajectories, but 3I Atlas showed zero non-gravitational acceleration throughout. Exit deviation cannot result from outgassing producing no effects elsewhere. The implication proves inescapable. Something changed the path in ways passive processes cannot explain. Whether through controlled propulsion, gravitational manipulation, or unknown physics, the object altered trajectory with precision, suggesting purpose rather than chance. We end where we began, with silence. Not empty space silence, but silence of something that visited, observed, and departed on its own terms. Telescopes watch, data accumulates, and somewhere between the measurable and impossible, truth waits for humanity to become ready. The question isn't whether we're alone anymore. The question is whether we're ready to know.